So let's restart and close on the BGP theory part. I think there was some typos in the slides. If we correct the typo, I mean your answer was correct, but there was some inconsistency. Here is the corrected version that will be put online later today. We've seen that for the principle of BGP is that inside a domain, all BGP routers should talk to each other over what is called the IBGP mesh. Second, we've seen that in practice, in a domain, you want all routers to speak BGP if this domain has BGP peers somewhere. So that you start having perhaps a problem, a scalability issue. Do you really want all BGP routers inside a large domain to speak to all BGP routers inside this domain? In theory, yes, but there are ways to go around this problem. One, and there are essentially two ways. One of them is called confederation. That's the one that's given here. Assume you have a very large domain, then you can break it into subdomains, give private AS numbers to your subdomains, and do as if they would be different domains, and use BGP between the different domains. So here between, on the top, ASP1 and ASP2, we would run what is called eBGP, even though it's inside a domain, but it is considered as external inside the private ASP1. Because if I have a collection of domains, there is no requirement that I have a full mesh of BGP peerings between all the routers. Of course, we won't have that in the world. So here, the top routers need to speak to each other of the top routers. Then inside their domain, you have a full mesh. Between domains, you have simply connections to the others. So in some sense, you fool BGP to believe that it is made of a collection of small domains. Of course, you need to remove the private AS numbers out of the AS path when you speak to the outside. So here, when this router speaks to the outside to a true eBGP peer that is truly outside of Z, you will need to replace the AS numbers like P1 by Z, for example. So that is one possibility that is used. For some reason, that seems to be the simpler. For some reason, there are variants of that which are called route reflectors. So route reflectors are a variant of the previous method. The confederation method has the problem that the vocabulary used by the confederation doesn't match what you see in reality. You talk of an eBGP peer that is in fact inside your domain, but outside your private domain. So perhaps in order to avoid these confusions, a variant is to do a special protocol, which is called the route reflector protocol, that allows to break truly the IBGP mesh by saying every BGP router inside a domain elects what is called a route reflector, and all the routers in cluster 1, so there has to be a clustering algorithm, they have a connection only to the route reflectors, and all the route reflectors do a full mesh. But you don't have a full mesh from any BGP router to any BGP router. All we need is that the route reflectors form a full mesh, which are in some sense the delegates that are used by the BGP routers. So you need special attributes to do that and to elect the cluster head. And also, as you can imagine, you want a protocol to make sure that if the cluster head is dead or doesn't respond, there would be an election of a new cluster head. So we could discuss that in detail, but we won't do that here. So you will see sometimes the concept of route reflectors. A remote concept is that of route server. Route server is often confused for route reflector. That's a different thing. The route server is something that is used to avoid the eBGP mesh. Well, I just said there is no eBGP mesh. Well, in general, there is not. However, there are cases where you can see in a room a lot of BGP routers that speak that are not in the same domain, but they are in the same room. This is what is called Internet Inter-Exchange Point, IXPs. I'll talk about it in a second. In such a case, you have perhaps in the same room lots of operators of ISPs, perhaps 30, perhaps 100, perhaps several hundreds, that connect to each other. So they each come with their router or with a slice of router, and then they need to connect to each other. They need to connect to each other because they are peers, right? If Swisscom, Sunrise, and France Telecom are in the same room, they don't accept to go through France Telecom because they are not customers. France Telecom is not providing transit service for those two. So they need to connect to all the peers. So you have what is called the eBGP mesh in such a situation, which might also be a problem in a cabling and space problem. So you can do the same trick, which consists in having a cluster where instead of speaking to all eBGP peers, and instead of using another AS as transit, you agree inside this room, you put a little money in a common pot, all the different participants, and you buy one router that you share between everyone, and you call it a route server. And that is essentially the same idea as the clustering that we have seen for the iBGP mesh. So we won't see those things in detail. That gives you an idea of the kind of optimizations that are present. The route servers are typically computers that are run in what is called an inter-exchange point. Inter-exchange points are things like, this is a vision of Switzerland, simplified vision. You have inter-exchange point like CIXP in Geneva and in Zurich, Swiss IX. Those are those rooms where a lot of providers meet with each other in order to peer. Whoops. And if you want to do that tomorrow because you start an ISP business, you can go, for example, to Swiss IX, and you would pay fees for interconnection. And those are typically non-profit organizations that just share the costs. In other countries, like the US, they are for-profit organizations. And you also have direct links between, for example, Switch. This is a map of the Switch network, has a direct link to other providers like Swisscom instead of peering in an exchange point. The AS number of Switch is 559, as we have mentioned, and here is a view of the world seen from EPFL, or more precisely from Switch, from 559. So you can see all the ASs that are directly connected to Switch, that are 2 hops away from Switch in AS count, etc. So this is the complexity of the internet seen from this place, or from Switzerland, and counted in ASs. Of course, when we count in ASs, some ASs are very large. So one point on this map might be something like level 3 of Sprint, a huge provider that has a worldwide presence, or a minuscule provider that like Switch, that provides a service to a relatively small fraction of the internet. Google is also one of those guys. Some statistics. I mentioned 500,000 entries. If we go to the routers that are at the core of the internet, that's what we're close to that. I mean, it varies a lot. It varies a bit, but it grows and is getting close to 500,000 IPv4 prefixes that are in the BGP tables. Of course, there's also the IPv6 prefixes. If we look at the statistics of AS of Switch, we see how serious IPv6 is at aggregating. We see that the Switch forwards to the rest of the world, announces to the rest of the world 95 IPv4 prefixes, but only 5 IPv6 prefixes. So we have a better aggregation with IPv6 as expected. So we hope to have fewer prefixes thanks to IPv6, but of course, when we introduce IPv6, we go in the reverse direction. We have all the IPv4 prefixes plus all the IPv6 prefixes. So we're not really making things better for the time being. Voila, that's all we will see on BGP, at least for the theory part. And then tomorrow you can start playing with that in your computer and see how to do all of this in practice. Questions? Then if there is no question, we move to the announced next topic, which is the application layer. So we jungle with the layers and go up the hierarchy and talk of the application layer. We won't talk much about the application layer because it's not the focus of this course. However, there are still things to say, and one of them is the DNS that we've mentioned already, that we can view as parts of the application layer. The other is application layer gateways. But of course, most of the application layer is about the application themselves, and that's the topic of lots of other courses, information systems, distributed systems, just to mention a few, databases, etc. We've done an application layer in Lab 2. You've done a toy application layer, so you have already a feeling of how it is. But of course, I insist again, much of the problems of the application layer are in the application logic themselves, and they are not the focus of this course. Application layers typically have to do a protocol. For example, in Lab 2, the protocol consists in the rules of the game. We expect the server to receive a message and echo it back to another client. That's the definition of the protocol. One application layer is the web. The web has one protocol, which is HTTP, which is a very simple protocol that consists in sending a message with a few possible verbs, words inside the message, like post, get, and what is expected behavior. If you send a get, you're expected to receive a file back. This is what this computer is doing here. So any protocol will have that, any application layer will have a protocol, because you need to define the rules of the game between the communicating entity. Typically, there are other things that are necessary to solve, like the format, the data format. HTML is one, but as you know, there are zillions of other formats used in the web for video, for images, etc. And there is also a naming issue that we will discuss more when we talk about DNS. An application layer needs to use TCP or UDP. Today in the internet, there's no other choice. There are a few applications that sit natively on the Mac layer, but they are a bit disappearing. So typically, we will use one of the two, like we did in Lab 2. We use TCP if we can. That's the default choice, because using TCP will relieve us from manipulating acknowledgements and things like this. HTTP uses TCP, as we've seen before. So when we send a GET, which is the only visible thing at the application layer, in fact, before that, there will be 3 packets exchanged. So between my client and the web server, there will be opening of a TCP connection. So 3 empty packets, 2 one way, 1 in the reverse direction. And only then we will send the GET in 1 packet, and perhaps a large number of packets to get the information. URLs are essentially, well, we've seen that already, are essentially the name of the local machine and some application-specific information. For example, the path in the file system of objects, if it's a web client talking to a web server. Now, a few things perhaps we've seen already, but I repeat them. In principle, we can use addresses instead of names. Addresses and names are, in principle, one-to-one mapped by DNS. So you can speak to the LCA web server by connecting to its IP address, IPv4 or IPv6. If it's IPv6, typically we put brackets. We can also specify this, which is what? A port number. So of course, if we put the column for the port number, we need to make the difference between the column used inside an IPv6 address. This is why we use the brackets with IPv6 address. A few bizarre things. protocol like FTP or the variants of it, which is used for transferring files, FTP without any security, SFTP with some security. Here is a possible way to use FTP called the active mode. In this way of operation, we connect to what is called an FTP server over a connection that's used for control. FTP is a file transfer protocol like HTTP, but much more. FTP allows to navigate in the remote tree file system. So it has a control connection which allows you to have a shell in the remote machine, and this is done using port 21, which is the server port for FTP. Then when you do that, you have a special set of commands like ports that instructs the client to be ready to open, to receive an open connection, a TCP connection being open on the port number that is instructed by the client to the server. Or you can do the same thing but in the other direction. The second TCP connection that will be used to do the actual transfer can be open from the client to the server instead of from the server to the client. This is called passive mode, FTP. Now in those two cases, which of the port numbers are server ports, TCP server ports? Which of those three ports mentioned in 1, 2, and 3? Five more seconds. I'm closing the poll. And the correct answer is not the majority vote, but is number 7. All of the 3, you've done the TCP programming lab. So if we are, so 21 is a server port, it's waiting for a TCP connection to be open. Sorry, open TCP, I said, I would fail the, sorry, the, so let me backtrack and delete this one. So 21, is 21 a server port? Yes, because we open a TCP connection to 21. If I write the code here, I will need to open a socket and do listen on 21. Right. On 20, will I do a listen? No. No. I will do bind, of course, but I will not do a listen, right? I will directly do a connect. I will connect to 1, 2, 3, 4, 6. On 1, 2, 3, 4, 6, I will do a listen. In fact, the client, the logic of the FTP client is I start a server port, I look which port number I get from the operating system, in that case 1, 2, 3, 4, 6. I inform the FTP server of that port number, and the FTP server connects to me. So 1, 2, 3, 4, 6 is a server port. Right. 20 is not. So the correct answer is 21 and 1, 2, 3, 4, 6, which is, shame, number 6, the correct answer. But I share your confusion. So the correct answer is 21 and so only this one. Well, this is illustrating again that at the application layer, being a server means listening for a request to come, does not necessarily mean being a server at the TCP layer. You need to be more careful. Of course, this way of doing FTP is a bit weird and is very often doesn't work because many networks, many routers will kill the TCP open connection coming from the server to the client because they believe there is somebody trying to open a connection on a server that should not be in my network. We have seen in FTP, like in HTTP, that the commands are sent in clear text, which means if you do a Wireshark, you will see, and if you do an ASCII print of the content of the packet, you will see the commands. They are not encoded using binary or complex things, which is a general rule to simplify. That was done at the beginning to simplify the operation of the application layer, but you can play with it. You can use the telnet command to a machine. 25 is the port. By doing that, I am manually connecting to a mail server on my machine, and I can send and see the commands on this machine. So clear text is often used. It can be used to debug a protocol. So it's a good idea to use human readable commands in a protocol, but of course it makes also the job of the attackers easier. That's all we will see about the application layer in general. Now there are two things we need to study in more detail. A few words about DNS. We've encountered DNS already, and those of you who are taking the research exercise probably had to dive into it more. DNS was invented because IP addresses were believed to be not human-friendly. Now, perhaps they're more human-friendly than names, but that's another story. So it is the directory service of the internet. The essential job of DNS is to replace an IP address by a full name. For example, ssc.epfl.ch, which tells me more about the machine than an IP address. It says to me, well, that's epfl.ch, it's in Switzerland, it's at EPFL, and SSC probably means something I can say. DNS names are standardized by the IETF and IANA. They are based on a hierarchy, a complete naming system, where at the top we have a number of predefined levels. Until this year, there were only the levels that are given here, like the two-letter two-letter levels are typically are country codes: CH for Switzerland, LE for Liechtenstein, ZA for South Africa, US for USA, etc. And then another number of so-called top-level domains are for areas that are not based on countries. For example, the most famous .com is for anything that is commercial. .net is for anything that has to do with the internet itself. .org for non-profit organization, etc. Recently, you can even, if you're a line of 500,000 Swiss francs, you can buy your own name as a top-level name, like Nestlé. If you're Nestlé, you can use it, which is probably a nuisance, just a way for the registries to make money by selling essentially something that's completely virtual. Then, once you have, for example, CH, somebody in the world, the organization in the world that receives from the Swiss government the mandate to manage the domain name for Switzerland, receives the .ch part of the tree. And then it can delegate to whoever asks for it and pays 17 francs a year for a domain. For example, EPFL has one domain, so it pays to the entity that runs CH, which happens to be Switch, 17 francs a year to get the EPFL. And then inside EPFL, the EPFL system managers can delegate further names. Inside EPFL, there's no other subdomain. So a name of EPFL is typically a name like LRC Sunnes, .epfl.ch. At our daughter school, ETH, in Zurich, there is further subdomains. So every department has its own subdomain. So you can have, for example, tic.ee.ethz.ch. So that is the general delegation principle. Yes?
Why isn't the edu prefix used for EPFL?
Why is the edu prefix used? Not used for EPFL. So edu is in principle education. In practice, it means American University. Now, whether EPFL wants to get an epfl.edu, they can if they want, if they pay for it.
Works actually.
Pardon me?
They have it.
They have it. Yeah. So epfl.edu exists. Okay, I didn't know that. Thank you. So, yeah.
So you just need to be a university. There are no restrictions.
So every top-level domain dictates his own restrictions, right? So typically, if you are .Nestle, then you control entirely. Hopefully it's sold to the Nestle company, right? And then Nestle will decide what to do with it and will not accept that EPFL has an epfl.nestle, except EPFL has a research lab with Nestle, whatever. Okay. So similarly, Switch has rules for who is allowed to have a .ch domain. Those rules are very loose. You don't need to be in Switzerland. If you pay 17 francs a year, which is more expensive than most other domains anyhow, so probably you have a reason to have a .ch. Probably perhaps you sell cars and you want Volvo.ch because you want to have a website for the Swiss people. You don't need to have your server in Switzerland. You can have zero. But you need that this address is agreeable to Switch. For example, if you're not Volvo and you want to have the Volvo, perhaps Switch will check and say, well, why do you want the Volvo name if you're not the Volvo company? So every domain will try to do their own thing. Some domains don't care, like Libya, which is .ly. They give any domain to anybody because that makes common words in English that terminate with .ly. Right? So this is essentially business, right? Every domain name is in principle English ASCII names, where capital lowercase letters. So if you write EPFL capital E, capital P, it will be the same as little e, little p. There is recently also the possibility to have non-American or English ASCII letters, like this one here. You can have French or German style umlaut or accents, which are in fact translated through a fairly complex coding mechanism called the Punycode. They are translated into ASCII names. So this one is in fact the same as this one here. Right, so there is a translation, a coding mechanism that would translate anything non-American ASCII to the standard ASCII. How does DNS work? Right, let's look. DNS is an application that in principle runs on UDP, but you can use TCP also. It will just be longer. Typically use UDP because you send one short message and wait for the answer. So you will anyhow wait for the answer, and if the answer doesn't come, you will try again. So the acknowledgement is in fact the response. So you don't. That's a case of a protocol where the stop and go protocol, send for something, wait for the answer. If the answer doesn't come, send again. The application needs to do that anyhow. So we don't need TCP. But you can use TCP as well, and this is typically used if we use DNSSEC, where we put more bells and features for cryptography. Here is Lisa that has clicked on her browser on she wants to find some research paper done by zurich.ibm.com. The browser will need to translate, so the The browser understands that the beginning of this, HTTP means I use the HTTP protocol, and what comes next is the name of a machine, the name of the web server. So I need to translate that to an IP address. The browser will use a DNS server that helps us. That's part of the configuration that you had to struggle with in Lab 1 and Lab 3. You need a DNS server configuration in your machine. What is this DNS server? Typically, it's the one provided by your environment. If you're at EPFL in a given room, there must be a DNS server configured in your machine, which is an EPFL DNS server. You can use also Google's DNS server that puts it at disposal of the entire world. Of course, by doing that, they will be able to sniff all the requests that everybody does. So there's some interest in doing that. And this server is called recursive, or more precisely, the query will be sent by, when the web browser has this to do, it will call a program called the DNS resolver that has the job to translate a name to an IP address. And the only thing it can do is send a DNS message to a DNS server, which is what it does. So it sends this query, and this query says, recursive RD, recursivity is desired. Recursive means what here? Well, it means that I would like the DNS server to solve the problem for me, which is what it will do. So the question is, what is the address of this machine? The capital A means what is the IPv4 address. Then the DNS server of EPFL, who is not IBM. So this address is in the IBM.com domain. So it doesn't know what to do. If it would be an EPFL.ch address, it would know and would give the answer immediately. If it's not, then it will follow the hierarchy. It will go to the top of the hierarchy. So in principle to the .com. So it will go to the root name server. The root name server is the servers that are at the top of the hierarchy that knows who are the the name servers for all the top level domains. They know that for .ch it is a DNS server at switch. So they will know that for the .com it is whoever runs .com. Now it turns out the root name servers also serve .com. So by sending the request to here, we will get a response from 3 that is something like this. So the root name server has not done the job. So it is not handling the request in a recursive manner. It is doing what is called an iterative manner. Iterative means I will give you one help that will help you to go forward, but you will need to do it again. So what is the answer? The number 3 that is coming here. Well, the answer is saying, I don't know this address, but I know who the name servers for IBM.com are. And I give their names, which of course is completely useless because I don't know how to map their names, but of course they give in addition their IP addresses. So here, what the root name server has given to the EPFL resolver is 3 IP addresses of 3 servers in the world that are what are called authorities for the IBM.com domain, that are run by the IBM company, probably, for such a large company. So my server here, which is doing a recursive job for me, will try again. If the server would be iterative, it would not do all that. It would just respond to me what is the address of the root. But because it's recursive, it does the job for me and will send the same request again to, well, one of those. So it picked the first one, Watson. Number 4 is the same query. And Watson now, which is inside the IBM domain, knows the answer and will give me the address, which is this IP address and a number of other fields. Another field like 7200 is a time to live, and A is the type of the record. I've asked for an IP address, I get an IP address. Then the DNS server will inform me, and then I have the information. Of course, this might take some time, and it is recursive because I sent one response and I got the answer, and the server did it again and again. For LRC SUNS, things were not recursive. For Lisa's computers, they were recursive. Now we can go directly into our machine and using, for example, programs like NSLOOKUP or DIG, and ask and see what the resolver would see. For example, I did that here. I asked, give me the A records for lca.epfl.ch. Here are the answers I obtained. I obtained the A record here. Then there are many other records in the DNS, but the only interesting ones we will use are really the A records. And some of them are called canonical names, which means that sometimes machines have several names. One canonical name, which is the name seen by the system manager who configures and runs the machine, and other names that are the names corresponding to the services. In this case, LAC1 server2.epfl.ch happens to be a web server for lca.epfl.ch, and perhaps does other things. Perhaps it's providing a cloud service or an FTP server. And here is the address. I've asked here for an IPv4 address. I could ask for an IPv6. An IPv6 is called a quadruple A record, 4 times as many bits as an A record. So if I ask for that, I will get it. I will get this IPv6 address of this machine. And I also always have a time to live here. The time to live is the way by which the organization control how dynamic their addresses are. Because when receiving message 5, the correct answer, the DNS resolver of EPFL will forward the answer to Lisa, but of course we'll try to optimize a bit the system by saying if someone else goes to ibm.com, perhaps it's Lisa that will do it again, perhaps it's someone else. It's a good idea to cache the recently received answers. So that, in fact, most of the time, what I've shown here will not happen. Most of the time, somebody has done it before, and the most recent result of this process is remembered by the DNS server of EPFL. But of course, we want to control how long this is kept. So there is a so-called TTL. So when Watson responded to EPFL, it also gave a time to live. Be careful, this has nothing to do with the time to live that's in the IP packet. It is the time to live of a DNS record in a cache. It could have a default value, but it is not. It is controlled by the server. So in this example, it gave 7,200, which means 2 hours. It's in seconds. That means you can keep that during 2 hours. If any other request comes to the DNS resolver of EPFL, in the next 2 hours, the DNS resolver will not do anything, will not go to IBM again. It will respond with the same answer. After 2 hours, it will consider that the entry is stale, is no longer valid, and will try again. So here, Watson, which is the authority for this, has decided about the TTL. So typical things like IBM will take a few hours. If you go to Google addresses, they will be much faster. There will be perhaps 1 or 2 minutes because they want the thing to be more dynamic. So this is illustrated here, that if we go to the DNS server a bit later and we see the answer, then we see in the answer the time to live, which is, this was done 1 minute later, so it is 60 seconds less, and Bart will get the same answer. Right. So this is the basic operation of the DNS, and that's the way it is today. And surprisingly, that's all about DNS. Right? So the entire internet depends on DNS. When you go to Google something, what you get is a URL. So you have the name of a thing and you click on it. Right? So everything goes through the DNS, and the DNS is, most of it today, unsecure. Which means that there are a number of attacks that are possible, and perhaps we will know more about it when we see the results of the research exercise. So anybody can send pretend to be the IBM DNS server, for example, and fool the EPFL machine with incorrect answers. Right? So there is, of course, a solution to that, which is DNSSEC. And the idea is that you don't simply go to a server and say, aha, here is the IP address of IBM.com, but you may want to sign this using certificate technology, asymmetric cryptography, and so that you can verify, much like when you go to your bank to do e-banking with HTTPS, you can similarly sign and see whether the record that you get from IBM, which has a signature on it, then you have, through a chain of certificates initialized in your operating system, you can have the public key of IBM DNS, and then you can verify if the signature is correct, which means that the record that you've received was really signed by IBM. So that can be done, that is done. Some countries like Sweden and most of Germany implement it systematically. At EPFL, surprisingly, we don't do it. Right. So we'll come back to DNS a bit later, in particular in the research exercise. There is an alternative to DNS that is called NetBIOS or Bonjour. NetBIOS is the Microsoft version and IBM. Bonjour is the Apple version. There is always two ways to solve a naming problem. One way is using servers. We have seen another instance at other places in the layers where we had a similar problem. ARP, exactly. I have the IP address of the next hop, and I need to have the MAC address. So it's not a naming, but it's very similar. I know with some designation a machine, and I need another designation. With ARP, except for some special cases, we don't use servers. Instead, what do we do with ARPs? We use broadcast with IPv4, and with IPv6, the same, but multicast. Right? We can do the same for DNS. And the typical case is called the dentist's office case. You have a small environment where you have a printer and you want to connect to your printer by a name, not by its IP address. So you go to, for example, HP Laser 2719, which is visible on the printer because it's the name of the printer. And then you would like to print to it. Well, you can do it. There's a special high-level domain, which is called local, which means anything that is local in a given private environment. And then we can use, very much like ARP, we can use a DNS replacement, which I call the serverless DNS, which is using the port 5353. That's an analogy to the 53. And it uses multicast. Now, if you are in a domain where multicast is supported, like EPFL, that means you can discover any printer by its name. Of course, you have to make sure you don't have two printers with the same name, right? Or if you have two, then you're happy with that and you want to take any of those. In most places, at EPFL, we support multicast, but we're an academic environment. That's a bit unusual. In most places, multicast is not supported by routers. We'll discuss that a bit already. But it is supported in one LAN. So typically this works if you're at home, you have a printer, a few computers, and your iPhone wants to find the printer, then in your local environment, the multicast will be supported typically because they are served by broadcast. So this is an alternative to DNS, small scale. Voilà, that's all we'll see about DNS, and we'll conclude with a small question. Here, we run a web server that you've tested on IPv4, IPv6 on lca.epfl.ch, and then our machine crashes, or we install the newer one, so we change its IP address. We could keep the same IP address, but typically we don't do that. We prefer to give IP addresses to our servers that correspond more or less to the physical machine, as long as it's working. How long will it take for the rest of us to go to the new machine? I close the poll. I think it has to do with the bell. F4. And the correct answer is 1 day, that we can read here, so it's more arithmetic exercise. This is the number of seconds in a day, which is also the default value at EPFL. And this is how DNS works. Voilà, that's the end for today. Have a good lab tomorrow.